I am Pranay Goel. I will tell you about electrophysiology models, and Professor Sitabra Sinha will tell you more about networks of these neurons and so on. So between the two of us, hopefully you'll get a good sense of neuronal networks, dynamics, and that sort of thing. So before I start, I want to make a couple of announcements. As you can see, this is going to be largely a chalk talk. So I'm going to use the board very informally. And if you have any questions at any point, if I'm going too slow, I'm going too fast, please feel free to interrupt me and tell me so that I can adjust my pace accordingly. Right? I won't know right at the beginning how fast I should go. I'll just go at my own speed, and then at some point, your feedback will help me adjust that. Okay, so there's going to be I plan to do a tutorial at some point in the week. I'm here for the entire week, as you all see from the schedule, and at some point I want to talk to you about a software package where we will be able to implement, where you will be able to implement the equations that I'm going to show you, and you'll be able to run a little exercises, and we'll have a tutorial session where I can help troubleshoot, debug, you getting there. So the goal is for this to be an interactive session, all of them to be an interactive session. We'll have a tutorial where you can implement the sorts of equations and models that I'm going to show you. Okay, now let me tell you a little bit about the content of what I'm going to cover. I want to cover essentially what are known as the celebrated Hodgkin-Huxley equations. Right? Anybody, raise your hands how many of you have heard this word and like to know more about it, or only heard about it? And the others have not, I assume, or you're just being shy. The Hodgkin-Huxley equations are Nobel Prize winning equations which basically describe how electricity in the nerve cell works, right? And these are celebrated because they reveal a very fundamental aspect of all cells in the body. Okay? And that is that all cells in the body are charged. They have an electrical charge in them. Okay? Some of them do very wonderful things with these charges, and we'll describe how these things work. And so, and it's going to take us a while to get through the equations and see what these wonderful things are. And then all networks, computing, thinking, those sorts of things will be left for your creative minds to discover over the course of a career. Okay. Before I actually get into the instruction, I want to get a sense of what your backgrounds are. So just raise your hands to let me know who is an applied mathematician studying something in applied mathematics, somewhere or the other. Okay, so the people who haven't raised their hands are they physicists? Or did physicists already raise their hand during the applied math question? You're going to have to be a little bit more responsive than that. I know it's early, but okay, how many people are studying biology programs and don't have too much mathematics background? I see. Okay. Are there people who are not completely comfortable with differential equations to begin with? Is everybody comfortable with differential equations? Just basic coordinate differential equations? Okay, if you are feeling shy that you don't understand differential equations so on, what I suggest is, in fact this is true for generally for everyone, please find somebody you can talk to, during one of the breaks and so on, and use them to interact with them to help to learn things and to brainstorm, teach things and so on, right? So in general, interact with yourselves, that will be a good thing, and interact with me, find me over lunch or one of the breaks or anything, and ask me any question. No questions too silly to answer, okay? Unless you're asking me about ESP or something, in which case please don't ask me. Okay, so let me start by telling you a little bit about the exciting times we live in. The generation previous to me saw transistors, and that's a revolution, right? You all realize, or you probably don't realize because you're too young, what a revolution transistors was, right? My generation has seen some revolutions of our own. For example, we've seen truly, genuinely artificial intelligence systems come up, right? Artificial intelligence has been a dream for many, many decades, right? And for the first time, we are starting to see truly artificial intelligent systems. The stuff in your phones, for example, which will automatically recognize when a person's face is being flashed on the screen, or things like your smartphone application where it starts to suggest what your answer to your email should be, and often gets it right. Right? Those are genuinely remarkable things. But more to the point, there are also systems in medicine that have come up. And there was a recent report in Nature, for example, that showed that if you take pictures of skin disease, especially cancer, then the kinds of accuracies you could get by automated reporting of when something is cancerous, when a person has cancer or not, could be as good as some of the best dermatologists, which is remarkable, which is fantastic, which is amazing. And it's all the more amazing because people didn't build these algorithms by sort of feature selection, what's called feature selection. You don't actually pick out features of the particular cancer and try to say that, oh, look, if you had that particular feature in this redness spot over there, then that's probably likely to be a cancer. No, it was not that. What it was they showed a lot of pictures of cancers and non-cancerous skin images, and the computer program learned over being trained for which of these were cancer and which were not by a human, of course, and over a period of time, the computer program learns it, right? The algorithm learns it. So this, to me, is genuine artificial intelligence. Of course, it's in a very limited sense, and you're welcome to discuss with me along these lines also. Why is it limited? What is remarkable about it, and so on. Okay, but that's not the point of this story. The point of the story is there's going to be something remarkable that's going to happen in your lives. You, for the first time, will see, most likely, my prediction, you will for the first time see truly, genuinely neuromorphic chips. Let me tell you a little bit about what that means. Okay, maybe I will have retired by then, or maybe it will be as I'm retiring and you will see them for the first time. So here's what I mean when I see genuinely neuromorphic chips. Today, you can't walk into a store, you can't go into Amazon and buy a chip and say, this chip, you've all seen ICs and things like that, I assume, right? Even though you're mathematicians, you must have seen something of those types, right? So you can't walk into a store and say, well, this chip is a neuron. This chip is a synapse. How many do you want? Give me 5 neurons and 5 synapses, right? And then I put it on a breadboard, connected up wires, and look, I have a little tiny brain working here, right? The kind of brain that helps locomotion, the kind of thing that helps little fish swim, or little worms move. You can develop these things if you had chips. So why do you think we don't have chips like this? I predict that kind of engineering will occur within your lifetime. Anybody want to give a sense of why you don't see these chips right now? I mean, these equations, the ones I'm showing you, are what, 40, 50 years old? You could have seen this now. You could have seen it now. I'll give you context, right? When I was growing up, we used to be able to go into a store and buy, transistors and resistors and capacitors, and you hook them up using a breadboard and wires and little batteries and little switches, and you could see, flashing lights going bing bong, bing bong, bing bong. That's also the sort of thing that my kids enjoy doing. My elder kid does this, but he has more stuff available to him. Now we have Raspberry Pi and Arduino chips and so on. What those chips allow you to do is they allow you to do computer programming. So there's software integrated along with hardware. So now you've got these software hardware hybrids, and that's what the current status is, right? What I'm suggesting to you is by the time you guys grow up, you will probably be able to have neuromorphic chips. That, by neuromorphic I mean hardware, software, and with the hardware of a neuron actually implemented on a chip. Anybody want to suggest, but we're not there yet, anybody want to suggest why we haven't gotten there yet? Why don't you have departments of neuromorphic engineering at IIT Chennai? Why are we not having this talk? by we having at IMSC rather than at IIT Chennai. We could have had departments. We had programs like this. We had things like SPICE and so on. I don't know if anybody knows what a SPICE program is, what SPICE is. I'm not sure if it exists now, but I'll tell you what it was. If you wanted to do very large scale engineering, the kinds of stuff that goes into, you know, your smartphone or a computer chip or something like that, you could actually take, you know, you could either take transistors, little physical devices, get big, you put them in this thing and you hook them up and you make, you know, beds of transistors and things like that. Or you could go into this software program called SPICE, which would simulate the effect of what you would get, the answers that you would get by actually doing them just on software. So you could do a software based VLSI, very large scale integration design. And then, you know, once you know you've played around with it enough, you could actually go in and then implement it on a chip. So then you pass it off to a manufacturing facility, and the manufacturing facility reduces it down, puts it on a small chips and gives it to you, right? Okay. But in principle, you could have done it in hardware, you could have done it in software. And like I said, you have Raspberry Pi, and where you do it in hardware and software. At the moment, neuromorphic chips are implemented only in software, and that's the stuff that is going to be the what I'm going to talk about. I'm going to tell you, I'm going to show you electrophysiological models, and I'm going to show you in silico, in computer code, how to do it, or what it means mathematically, algorithmically, for you to be able to simulate the activity of a neuron, right? You don't have hardware chips. Anybody, I'll give you 30 seconds to give me a suggestion. Why do you think it's not available right now? I'm going to, let me give you a hint, you know, it's made up of capacitors and resistors, so it's passive electronics. The stuff that I'm going to show you are going to be the equations of passive electronics. Anybody? Anybody thought of that? So it's a great startup idea, right? Yeah, so form a company to market generally neuromorphic chips, right? Whoever gets there first makes $1 million or $1 billion. So Hewlett Packard has announced that it was supposed to be slated for early 2018 that they would come out with these chips. Where the essential component of a neuron would be available in hardware. So here's the answer. The answer is the neuron actually implements a very special passive resistor. How many people, a passive element called the memristor? It's one of the 4 known passive items, passive electronic items, right? Leon Chiva discovered its existence, postulated its existence hypothetically. I think it was in the 1970s, but I could be wrong. Please Google it and find out when that happened. Okay, and the implementation of a memristor, and I'm going to talk about this in detail. Not the implementation, the equations that correspond to the memristor. The implementation of the memristor in hardware is a very recent development. It was as recent as reports in 2008 or 2010, I believe, that Hewlett Packard, I think it was, where they announced that memristors on hardware implementations of memristors were available for the first time. And since then, over the last decade, there's been a flurry of interest, and lots of interest in developing hardware implementations of the memristors. So the point is that truly commercially available memristors are what you need in order to be able to build circuits that are genuinely neuromorphic, that are genuinely capable of reproducing electrical behavior, the sorts of things that you see in a neuron. Okay. At the moment, though, we are limited to software, but in a few years, by the time my kids have kids, if they do, they will be playing with neuromorphic architectures. Okay, so what do we need to get there? Well, we need to understand what the equations for the Hodgkin-Huxley equations are, because those form the core of what is it that a neuron is able to do, what are the sorts of behaviors, the dynamics that are possible with a neuron. And then if you connect neurons with other neurons, there's a whole other slew of what are known as emergent behavior, which is what Siddhartha will talk about, that are possible. And really the goal of all of this is to discover where the computations that humans are capable of carrying out come from. What does it mean for our brains that I am speaking to you and you were listening, and then you all will go on to do creative things and so on, right? And even you know, at a more elementary or more basic level, you know, what are the programs that are involved in, for example, smelling or seeing or hearing or sensing, touch and things like that. Just the very core programs that govern our senses, and then building on top of that some of the programs that are involved in computations that are more abstract, like thinking and representing a number and so on, right? All of those have neurological correlates. They are all implemented somewhere in our brains, in our spinal cords, in the nerves that carry the nerves that carry you know, impulses away, and so on. So let's start to look at that. Let's talk about what it means for a neuron to be active, right? A neuron is a nerve cell. How many people know what a neuron is? Just have heard of it at least? Everybody's heard of what a neuron is, right? We know nerves. So the cells that comprise nerves are called nerve cells or neurons, right? And just as a very crude mathematician's diagram, I'm going to draw a cell with a nucleus in it, because cells have nuclei, right? At least the nerve cells that we talk about, that we are interested in. And then this nerve cell has a long process, which again, you know, branches off into these things called synapses. So we'll talk about that in a bit. We'll talk about what it means for us. What am I drawing over here? These are called synapses. So this, just as a matter, I'm sorry. This is not a great drawing as far as biology goes, but it will do for us, right? So this is the cell body, the the center of the cell, the soma of it, and so on. And then there are long processes. This cell body is drawn into a long process. This is called an axon, which branches into dendrites. At the end of dendrites, you've got something called synapses, right? And synapses are where this neuron will connect to the next neuron and so on. So you will have one neuron talking to another and talking to another, and you will have a network of neurons, right? That's how neurons communicate. Right? We'll see in a bit what this activity is, but just very quickly, why do you think neurons have these many neurons? Neurons can have different architectures. This is just one prototype of the kinds of topology you see of neurons. Why do you think a neuron might have a long axon? Any suggestion? I should probably draw some dendrites on this side also. Anybody want to suggest why you can expect neurons to have long dendrites? Because notice what neurons do. Neurons carry signals, and we'll see what the signals are. How the neurons carry signals? The neurons carry signals from, say, your skin or your leg. In my toe, if I hit my toe and I feel against a table and I feel some pain, there will be some signal that has gone from my toe, traveled up my leg and gone into my spinal cord or my brain. Yeah. So you need to be able to carry signals across long distances. Obviously the neurons are there everywhere in the body. So neurons in the brain will have shorter processes, they'll have shorter axons, but some of the longer distance processing needs to be carried by neurons that can have very long axons, right? So just because signals need to travel over long distances, in some cases shorter, but in many cases long, you need to have processes which can carry signals. In other words, these things act like wires. Obviously, there's a lot of other stuff as well, you know, in cell body and so on. But you can think of these things as wires. So now, why do I call them wires? Wires deliberately, because these also carry electrical impulse. The way signals are carried is by carrying some form of an electrical impulse down the axon. Okay, so let's introduce this word. And we'll see what this means in a minute, okay? Now, if it were a regular copper wire, right? If you were to imagine that this was carrying electricity as in the usual way that copper wires carry electricity, say in this room, you turn on the switch, which is where the stimulus happens, right? If I turn on the switch over here, copper wires will carry electricity to these tube lights over there, for example, right? Now, can we take a minute to discuss whether this is the sort of thing that's going on in a neuron or not? What do you expect? Do you think that could be the way things happen in the electrical signals in a neuron? Anybody want to suggest something? The answer is no. That's not how things happen. How does it happen in a copper wire? Well, in a copper wire, if you've got a copper wire, you apply a voltage difference across the copper wire. Say this potential, this will be at a higher voltage potential, this will be at a lower potential, and this potential difference is what generates a current that goes through it. Okay. That is not what happens in a neuron. In a neuron, the inside of the membrane is charged relative to the outside. So which means that if you were to stick in a potentiometer, a voltmeter, everyone know what a voltmeter is? Measures potential difference, right? You'll have two wires, two prongs. You can insert it into a wall socket, for example, and measure one side being at higher potential relative to the other side. For example, if one of these you put into ground and the other one you put into positive, you'll see 220 volts or thereabouts. But that's AC. Okay, there is also DC and AC, but we won't get into that at the moment. You'll see in a neuron that's not stimulated, you will see the inside is negatively charged relative to the outside. So if you stick in a voltmeter and you measure the potential difference, it's on the order of minus 75 millivolts. The inside is negatively charged, the outside is positively charged, and this is going to be a little bit important for us. Just to have a sense of the magnitude, it's millivolts, obviously not volts, right? And it's about minus 75 millivolts. When I say minus, I mean it in this particular sense that the inside is a negative with respect to the outside. If you switch the sign convention, you switch the sign, of course. Okay, okay. So that's what happens. That's what the situation is for a neuron that's not stimulated. That's not carrying any particular signal at the moment, right? And remarkably, not remarkably, but just as a matter of fact, the cell actually goes through a lot of effort to make sure that the inside stays at minus 75 millivolts relative to the outside, right? So it has a whole bunch of nano machines that sit on the membrane, right? And these machines actually keep pumping ions out, exchanging them furiously. Right? So they continuously move ions around, and we'll see in a minute exactly what goes on over there, right? But essentially, this negative potential is coming out by maintaining a concentration difference of sodium and potassium channels, of sodium-potassium ions. So sodium ions and potassium ions, right? I'm writing them with a little plus charge to show that they are charged particles, that they are positive ions, right? The membrane works furiously through what is known as the sodium-potassium pump to make sure that there's a difference in the amount of potassium ions inside relative to the outside, and there's a difference in the potassium ions, sodium ions outside relative to the inside. And it is this difference that actually maintains a negative potential in the inside, outside, relative to the outside. Is that convincing? Do you think that that might happen? By moving charges around across the membrane, you might actually set up a situation where the inside is negatively charged relative to the outside. Yes? That sounds reasonable? Anybody who doesn't seem to be convinced by it?
So I just want to know if the issue happens that inside was plus,
yeah.
outside was minus,
Yeah.
and it was what would it have made to the electrical connection? Would it be the same thing?
Are you asking what happens when the inside becomes positively charged relative to the outside? Is that the question?
I think if the electrical state of affairs would have been the inside was positive
Yeah.
and outside was
Yeah.
Would that be still a possibility for impulse to flow, or no, it doesn't flow?
Membrane potentials are not designed to exploit that, at least as far as I know. I haven't seen any membrane, a whole cell membrane potential, which is positive inside relative to the outside. Maybe Sitabha can correct me. Have you ever seen any membrane potential that at rest is positive inside relative to the outside? I don't think so. I mean, that's you. It opens up all sorts of interesting questions. What would have happened? What would have been the biology had the membrane potential been positive inside to the outside? I'll have to think about it. But the way we're going to think about it is that the negative is, the way it is that the membrane potential is negative inside. Okay, and then we'll see what are the consequences of that and how if these the membrane potential does change. It's the at rest membrane potential that is negative, right? Okay. So where was I? Yeah, I was at the point where I was describing that the negative membrane potential does come about by maintaining a concentration difference of these charged particles, and that's kind of important. Okay. And it will become important, more and more important. We'll use this idea and develop it further and further to see what goes on over here. I started out by making a distinction between electrical wires and the kind of electrical impulses that take place in a neuron, right? So here's what goes on. I'll give you a brief nutshell idea of what this is. What happens is that there's going to be a local displacement of charges, which is then going to change the membrane potential. So you imagine with respect to the inside and the outside, you've got a situation that's under equilibrium. These pumps are working hard, and you maintain a difference. Okay, you maintain this potential difference. And then, what if something were to happen that this membrane potential difference, this concentration difference gets altered, and that will change the charge profile, and if the charge profile is changed, that will change the membrane profile, right? If the membrane profile changes, what happens to the membrane to the profile is that a wave is set up that travels down the axon, right? So there's a charge displacement, and something happens to the membrane potential. I'll draw it in a minute. That gets propagated. It happens here, then it happens here, then it happens here, then it happens here. It gets propagated down the axon all the way till it travels up to the dendrites. It stimulates stuff that goes on in the dendrites, and we'll talk a little more detail about what happens when it reaches the dendrites. And that's when an initiation of what is called an action potential. So this electrical impulse is going to be called an action potential. Okay. So a stimulation event, far up in the food chain, it could have been some stimulus, something you smelled that gets transferred into through a transduction process into some neuron, and then that gets transferred to some other neuron, so on and so on and so forth, till you get activation all the way up to your olfactory cortex, right? That propagation of events, the very element that underlies that is a neuron getting stimulated, generating an action potential at the hillock, at the cell body, which then travels down the axon into the dendrites, and that is then transferred to the next neuron. Okay, so there's these lovely events that are taking place. Now let me draw for you what an action potential actually looks like. So when I say I'm going to draw an action potential, what I'm going to do is I'm going to trace what it looks like in time for you. Okay, so this is going to be Vm, your membrane potential, and as I've defined it, it's V in minus V out. We realize what that means, right? That means the inside relative to the outside. I should point out that the inside is liquidy, gooey, so it's an aqueous solution, right? I like to think of the outside as like a salt water solution. So this is your cell, and it's bathed in some sort of a salt water like solution, right? And that is more correct than you would imagine, because actually this got a lot of salt over here. There's a lot of sodium concentration over here in the outside. Okay, so because it's an aqueous solution, that's important for us, because that means that the inside here, which is an aqueous solution, high in potassium, an aqueous solution over there, high in sodium, which means if there is an electrical activity generated here or there, that will get very quickly dispersed inside the cell, right? So this space becomes an isopotential. It becomes very quickly the same potential, okay? Because it's a relatively small space. It's an aqueous solution, so ions can move around very quickly. So the moment there is a charge separation over here, that effect, the resulting change of membrane potential, will spread out over there. So in other words, I can think of the membrane potential of the cell rather than membrane potential at that position in the cell or that position on the membrane, right? There's a homogenization that goes on with respect to the membrane potential. So this is at an isopotential. And then this space over here will locally be at isopotentials, right? So the moment this gets generated, something will happen over here, which will then move over there. So this stuff locally will be at isopotential, and so on and so forth. So you'll get a propagating wave over here, right? It's a little bit harder to see why this whole thing doesn't become isopotential, but that's got to do with the relative rate at which the membrane is changing to how fast things are spreading, right? There's an exquisite balance over there. So even though this stuff tries to become isopotential, the dynamics of the membrane changes are taking place on that same time scale. So they sort of constructively interfere with that, and that is what generates the wave. Okay, so let's go back to our diagram over here. So what I'm describing is at any one position over there, the membrane potential. The membrane potential initially was at minus 75 millivolts. This axis is time. At that location, at this location x, I'm going to draw a time profile of what the membrane potential will look like, right? Maybe I'll put it up over here, minus 75. So I get some space to draw. Okay, ready? So here's how it goes. You see an upswing of the membrane potential. That means the membrane is getting depolarized, getting more and more positive than minus negative 75. It goes up over here, right? And then it turns around. So the membrane potential has rapidly depolarized. What was initially minus 75 millivolts, boom, it became very quickly, it became positive. Right? And it goes all the way up to, it can go up to say 40 millivolts, positive though, yeah, plus 40 millivolts. And then it begins to turn around and swing back down. It comes back, it gets repolarized, right? Comes back down and overshoots. It swings below, it's kind of like a spring, loaded spring. You pull the spring out, it'll spring back, boom, it'll go past its own starting point. Swings back down, a couple of millivolts below, and then turns around and finally relaxes back to its resting position again. Okay, so at some point we will identify phases of this, but you already have seen some of it, right? So this is depolarization, that's a repolarization. This is a phase called after hyperpolarization, right? Or hyperpolarization and after hyperpolarization. Okay, so we're going to have to explain in dynamic terms, where does this come from? But let's look at it in the context of the propagating action potential. So at every such position, you actually do get an action potential that looks like this, right? And then this whole pulse, that's why it's called an impulse, right? This whole pulse, which occurred over here, happens in the next position and the next position, next position. You see a wave of action potential, this waveform traveling down the axon. That's what an action potential is. Approximately, yeah, for different neurons it's different.
Inside potential is better than outside potential.
Yes, correct.
So inside potential should always be negative.
No, it should not always be negative. The inside potential unstimulated at rest is negative, right? When the neuron is silent, it's not stimulated, it's at rest. That is the position called at rest. So, And that's what it is asymptotically, and that's what it is. I should mention that there are lots and lots of caveats which I won't describe here, right? Some neurons are continuously in the process of firing, some neurons are continuously at rest, right? So that is a network issue. But if you were to isolate a neuron, keep the environment is relatively stable so that this neuron lives and functions and so on, then that's the basic dynamics that you expect to see. Does this make sense? Hmm. Yeah. Yeah. Yeah, that's a wonderful question. Okay, great. So you bring out two very interesting aspects. One, where is the energy coming from and what are the energy changes that are involved here? Over here. Second, the point you make is this capacitor resistance circuits? Is this what is known as an RC circuit, right? In an RC circuit, you have a charging of a capacitor and then a discharging of a capacitor, right? That's for those of you who know what an RC circuit is, right? And that's what you mean by a build-up of charge if you connect. I won't draw it, but if anybody wants to talk to me about it, we can discuss it afterwards. You essentially have a circuit. When you throw the switch, the battery will charge the capacitor. Eventually, the capacitor will be charged to its maximum, and then you release or then you short the capacitor through some resistor and light bulb or whatever, and the capacitor will discharge it. So the capacitor stores the charge and you can get it to discharge as well, right? That is happening here, but in a very, very sophisticated way. Okay, let me point out that this is not an RC circuit. Fundamentally speaking, it is not an RC circuit, right? The kind of thing that you are thinking of is perfectly reasonable, and that's called passive dynamics. Very, very passive dynamics. I should mention that the memristor is also a passive resistor. In the interest of being, accurate about it, the memristor is also a passive resistance, but passive element. But you will see that you cannot get this out of an RC circuit alone. Okay, so it's not passive to the level of only RC circuits. I will also say that inductors are not used for some of this. There's a very small inductance in neurons, and it was discovered a very long time ago that inductors don't play a very strong role in this. So the magnetic effects of passive circuits are not an essential component of this. Okay. You do ask a question about the charge aspect of things or the energy aspect of things, and I think you meant it in the sense of charge being stored in the capacitor. But let me answer that question a little bit more broadly. Of course, this sort of dynamic will require energy, right? So where does its energy come from? Where does biologically, fundamentally energy come from? Anybody want to answer this? You probably know this, but let's just make sure we all hear it once more. Fair enough. I'm sorry, you say that again? The ATP potassium pump, sodium potassium pump is what? That's partly right, because like I said, the membrane potential is set up by the sodium potassium pump. But you have to answer, where does the pump get its own energy? That's the true source, right? Which is ATP. The ATP molecule. How many people know this? This molecule, have heard of it, right? There's a fundamental reaction in biological systems in which ATP, when it breaks down into ADP, adenosine trisphosphate to triphosphate to an adenosine diphosphate, ADP, that breakdown releases energy, and biological molecules, biological systems, cells, they use this energy, the free energy chain that's associated with this breakdown reaction to run energy consuming processes, things that would not be spontaneously active, use up this energy from the ATP. So there's something called an ATPase, and the sodium potassium pump is an example of a reaction that uses this energy that comes from ATP. Okay, so that's partly how you answer the question, where does the energy for all of this comes from. But even if you But if you do look beyond what the energy requirements of the cell are, which are no doubt there, genuine, you still have to answer this question by what causes this dynamics, what causes the membrane to go up and what causes it to go down and so on, right? There's a long history which I won't get into, but it's a fascinating history if any of you want to ask this question. And the history, nutshell, in a nutshell, the history goes like this. People have been trying to explain this behavior, what's called the action potential. People have noticed it for a very long time. Long time is almost going back 100 years now, right? Goel and Bernstein did some classic experiments on these things, and they looked for ways to explain this, right? The earliest theories felt that there was something about the membrane that was breaking down, right? You notice this rapid depolarization phase, right? That says that, you know, whatever process is there, which is working so hard to maintain this negative potential, is getting disrupted, it's getting broken down. So what would be the easiest? Making holes in the membrane potential. Now, if the membrane was breaking down, then, you know, you would dissipate the gradient, right? And in fact, you might even have it so that you actually reverse the polarity, make it positive, right? But membrane breakdown is accurate and not accurate, because one, if it's just a physical tear in the membrane, you would have to explain how it can get repolarized in such a short time space. This is on the order of a couple of milliseconds. The time scale on which this happens is on the order of milliseconds. This is extremely important. Okay. And it is related to the question that I posed just a minute ago. Why do you think axons have these long processes? Let's go back to that question. Okay. Given this, can you now re-answer my question? Why do neurons have long axons? Anybody want to attempt it in light of this new information that this action potential is taking place on the order of milliseconds? No, it's not about stabilization. Actually, my question is this. In light of this new piece of information that the action potential is acting, its entire polarization, repolarization phase, this whole time scale is on the order of milliseconds, right? Very, very, very short time scales. Can you reassess the question of the requirement why axons are long? Why neurons have long processes? Surface area, no. So if you draw a wire thin, it doesn't necessarily have a very large surface area. You could just have a large blob. That's right. So you're saying can pass the information for long? It can't pass it. But maybe turn that reasoning around, because the information is in the action potential. It's not that you're trying to avoid the action potential. The information, the useful information is in the action potential. So you don't want the action potential to be something that just, you know, you carry it out, get rid of it. It's everything is contained in the action potential. It's the firing of neurons that causes us to smell and think and things like that. It's the firing pattern, the activity in the network that we are after. That is what is causing the computer to work. That is the algorithm. Who, which, when neurons fire. The spatiotemporal pattern of firing in a network of neurons is the program. That's what you have to explain. So not wash it away, not wish it away. So the answer I was seeking was, imagine if I stubbed my foot, right? That information needs to be communicated, or I put my hand on something very hot, then I need to draw it away, right? That's a reflex action, right? That information needs to be processed by the spinal cord. Reflexes are processed by the spinal cord. Things that are on a slightly longer scale are processed by brains and so on. That information needs to be communicated really quickly. What other biological process can you think of other than electricity that can actually do this communication? if you think of diffusion, chemicals reacting and then those chemicals reacting to produce more chemicals that react and so on and so forth, then those diffusing, that will take a long, long time. By the time my hand will be burnt, right? If you want snap information, if you want information to travel real quick, how fast can you do it? You use electrical behavior, you'll use electrical impulses. That's why electricity is used in the body, okay? To be able to do things fast. And it's astonishing to me that the programs that allow us to think and smell and see and so on actually rely on fast information transfer. I mean, if you think about thinking through a math problem, you spend years working on something, right? There's no need for you to be fast. But the programs that allow you to do that, the processes, the biological processes are extraordinarily fast. They're sharp, they're really, really fast, right? The kinds of things that will allow you to run away from danger in an instant. Okay? It's just mind-boggling if you think about it. So you're carrying out very, 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 very fast processes for a very, 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 very long time. That's the process of doing maths. Okay, back to our action potential. Okay, so the question that we are beginning to answer, that we're seeking to answer, that the program that was carried out by experimentalists like Goel and Bernstein, and then finally answered by Hodgkin and Huxley, who gave a definitive model of how this happens, is to ask what is it that's going on in the neuron to actually allow for these processes to take place, to in particular allow for the action potential to take place. So here's what I'm going to do. I'm going to do the experiment mentally, which Hodgkin and Huxley, or maybe it was before them, I forget if the origin was actually Goel and Bernstein, or maybe Hodgkin and Huxley. But I'll tell you what the experiment is. The experiment is, let's throw out the propagation aspect of it from the picture, right? Because that's just an additional layer of complexity. I just want to understand for a moment, if I were to section off a piece over here, how does the action potential actually occur in that place? Because it's a localized event. It does take place at that position over here, right? That's a figure in time, right? At a given position, right? A similar picture will occur slightly delayed in time over there. That's the time propagation aspect of it. But what if for the moment, I want to chop this off and understand what happens at that location over there? That's a fair question, right? That's a question that physicists answer all the time. Okay, so here's an easy way to do it. Well, not easy way, but here's relatively easy way to do it. Is what they did was they looked for this, and I think this is definitely due to Hodgkin and Huxley. They looked at a marine animal called the squid. Excuse me. The reason to look for a squid is because it had a giant axon. They were able to locate one neuron which was so big that you could actually see it with the naked eye, right? And that's big, right? That's huge by microscopy standards, right? So by looking at the squid giant axon and isolating it, if it's large, then that means they have, they're better equipped to do it, to do experiments on it back in that day, and we're talking 1960s, 1950s, right? So in that environment of technological advance, they found a squid axon which they were able to manipulate. And what they decided to do was they got rid of most of the axon and inserted a silver wire down its length. If you insert a silver wire down its length, then what that allows them to do is, if they measure the potential of that silver wire relative to the outside, because the silver wire has a very, very high conductance, it shorts the entire inside, right? So you drop the propagation aspect out of the picture entirely, and this whole thing is now one isotonic, isopotential. It's one unit, right? So in other words, by putting in a silver wire, you've got yourself an ideal axon, an ideal neuron, a spherical cow, right? The idea that you're able to generate a single node of potential, right? Inside and outside are the only two things you care about. Everything inside stays inside, everything outside stays outside. The inside is at one potential different from the potential at the outside, right? So you're able to now do experiments using a voltmeter where the outside can be thought of as the ground and the inside membrane, inside is the quote unquote membrane potential. The inside is Vm. Does that make sense to everyone? Right? It's a very clever experimentalist trick to short the inside, isolate the inside relative to the outside, right? And then whatever you study for the properties of the inside membrane, inside potential is the membrane potential. You call it the membrane potential because it's the membrane that's keeping the potential inside different from the potential on the outside, right? So the entire trick is to have this bag enclosed by the membrane. Okay, does that make sense? And the inside is all going to be one membrane potential, one potential. This is going to be important to us because when I add some nuances on the membrane itself, you should be asking yourself, well, how do processes on the membrane communicate with processes on the inside? This is the cytosol, the liquid that's inside the cell, right? So, and the answer is going to be anything that allows potential to change across the membrane will be communicated very rapidly in the bulk. So, stuff that goes on over here will be seen by this very quickly, will be seen by this very quickly. Okay. That's how different positions in the membrane will communicate with each other through the milieu inside, through the potential that's taking place on the inside. Okay. And that is why stuff that goes anywhere, that goes on anywhere, the dynamics that goes on anywhere on the membrane through the membrane potential, through the inside potential will have a communication channel all at once. Does that make sense? And that's how different, what I'm going to call them, different proteins, I'm going to call them ion channels in a minute. Different proteins actually will be in communication on the membrane. Spatial heterogeneity is actually homogenized over by the inside being an isopotential. Does that make sense? Here's what I'm saying. I'm saying that if you imagine chalk here. If you imagine some protein that's on the membrane over there, right? You would imagine that a protein here has no chance of looking at a protein over there, right? Because this protein is embedded in this position in the membrane, that protein is embedded in that position in the membrane, right? And you would say that these two are independent. So you can imagine in your theory when we are going to develop that there's lots and lots and lots of little proteins studying the membrane, and together they are influencing the membrane potential, but they're all independent. But I'm saying that they're not all independent, they are coupled because any change that is transferred through any potential change that is occurring due to the activity of one membrane protein over here, because this is an isopotential, is also sensed by that membrane protein, right? Okay, so they are going to act in unison, they are going to act in coordination because they are in communication through the potential in the inside. Does that make sense? Okay. And for very small cells, you can do a little calculation to show that this communication is really, really rapid. It doesn't interfere with the time scale on which things are changing over here, just in the interest of clarity. Okay, so we are going to describe membrane potential changes as changes that take place in the activity of units that are studying the membrane. You're going to find that proteins on the membrane, changes in the activity of the proteins on these proteins, these membrane proteins, is what is going to cause this thing to change. Okay, so our goal now is going to be to study how we might describe protein changes. Yes. Oh, okay, okay. All right, let's talk about what a protein is. So let's go there. Let me describe to you what a membrane is first, and then I'll tell you what a membrane protein is going to be. So this thing that I drew for a mathematician, there's a little circle over there as just enclosing an area inside versus the area outside, is actually has a biological structure, which I'm going to, which let's take a look at, right? So this is actually a membrane. This is a layer. Think of it as a squishy, rubbery, plasticky thing, right? And it actually does have a structure like so. It has got one outer layer and one inner layer, right? And what are these inner and outer layers made of? They're made up of molecules called proteins, and proteins are molecules that are made up of proteins are molecules that are made up of amino acids. Amino acids are very basic units that make up proteins, and the structure of this is going to be okay. So there is a very special molecule that has, it's called a lipid fat, right? And it's got a hydrophilic head. Stylistically, you can describe it like this. It's got a hydrophilic head, that means it likes water, and it's got a hydrophobic, hating water, hydrophobic tail, right, which does not like water. So if two of these guys come together, they spontaneously assemble so that they line up their tails and point their heads away. They do this because if I draw a lot of them, you start to see why this happens. Anybody begin to see why this is happening? Like, because this side is water-like, right? This is the membrane. This little unit over here, that's this. Right? You got a hydrophobic head of these molecules, which align themselves with water, because water is here, water is here, water is here, water is here, right? And they all like water, so they put their hydrophobic tails away from the water, and then these tails point inside each other. And this structure, it's actually called a lipid bilayer. Bilayer because you've got two layers. And it turns out that this structure is stable. This structure is stable, it makes up this membrane, and it can go all the way around and keep the inside things inside and the outside things outside, like a thermos, except not with respect to heat but with respect to stuff that's inside the cell. So, right, it's a remarkable construction due to nature, of course, and across there are holes in the membrane where these complex pieces of molecules sit, okay, and they have the following structure. So I'm going to draw a molecule for you. I'm going to draw it a little bit stylized, okay. I'm going to draw it like so. What I'm trying to show is a molecule that is organized such that it allows for a passage through, right? And I'll talk to you about this a little bit more, right? There is a pore, possible pore, right? There is the possibility of allowing ion channels to go across, right? So positive channels, like say for potassium or sodium, right? They have the potential to pass through. Okay. This protein, a part of it sticks on the outside here and a part of it sticks on the inside. So this is known as a transmembrane protein for that reason, right? Transmembrane, and these things are molecules called proteins. And this specific protein is called an ion channel. Channel because it allows for the possibility of opening a pore. When I say possibility, I mean that sometimes it is closed, sometimes it's open, and we'll study when it's open and when it is closed. Right? This allows for the possibility that ions can go, but can sometimes be closed, in which case you won't have passage, or less closed or more closed, right? And transmembrane, because a part of it is available, is exposed to the outside, and a part of that same molecular structure, molecule, is exposed to the inside. So this allows for communication inside to outside. Think of it as a gatekeeper. Think of it as a gate that sometimes it can open, sometimes it can close, or sometimes it can be partly open, right? And it is accessible to all sorts of proteins. For the moment, we'll think of just sodium and potassium, because those are the essential ions that are there involved in the Hodgkin-Huxley axon. I should say at this point that there's a whole zoo of these of these ion channels, and when an ion channel allows sodium to go through, it's called a sodium ion channel. When an ion channel can allow potassium to go through, it's called a potassium ion channel. So in other words, ion channels are actually specific to which ion they are going to allow to go through. They could be chloride ion channels, there are calcium ion channels, and there are various types, various families. If you study the biology of this, you'll notice that there are various kinds of potassium channels with various properties, and there are various sodium channels with various properties, and so on, right? So there's a plethora of ion channels. We're not going to get in that kind of detail. What we're going to focus our discussion on is to ask, if there are a few channels, sodium or potassium, how do you use those to explain the action potential that you're interested in explaining? Okay. Complicated question, not only for chlorine but for all channels, because sometimes in certain phases of the ion of this action potential, things will be going inside, so in certain phases they'll be going outside. So we'll get to that in exquisite detail. That's where the game lies. What's going inside to outside when? Okay, there's no one answer to that. Okay, any other question on this? So what's our program next? So what I'm going to describe is, if you had channels, well, can you now explain what the configuration of concentration configuration of potassium and sodium would be, so that you can expect to see, for example, a negative membrane potential at rest, right? And then you would have to ask a more subtle, a much harder question, that how can you explain the up and the down and the full swing of the action potential, right? So the second part got a Nobel Prize, the first part is relatively easy. Does that make sense? Okay, shall we go on? Any questions so far? Okay, so let me tell you a little bit of an interesting anecdote over here. So the Hodgkin-Huxley model actually proposed that there should be these ion channels way before they were actually discovered biologically. It took almost 10 years or more for people to, for biologists experimentally discover that yes, these channels look like this and the crystal structure of it is such, and so on and so forth. Okay. So this is an example of where the modeling came first before the biology, and it's if you when we go through it, you'll see how remarkable it is that just by looking at the mathematics of it, Hodgkin-Huxley were able to produce these ideas. Because imagine that why should an ion channel allow for just one ion to go through, right? You might imagine if it's a pore, lots of ions will go through regardless of the identity of the ion channel, of the ion that's carrying the charge, right? It's open or closed to electricity, to charge, but no, it actually takes into account the where the charge is coming from, whether it's carried by a potassium or a sodium, and that's quite remarkable if you think about it, right? Okay, so let's do the first part first. So we want to explain, for example, how might it be that you can have a charge on the outside? Give me a quick answer for it. How can you expect? So we are going to use only two of them. We are going to use sodium and potassium, even though I know, even though I've said that in other cells and another neurons. You can have all sorts of other channels. We're going to use sodium and potassium because those were the ions that were used by Hodgkin and Huxley to explain how the action potential arises in the squid giant axon. Anybody want to give me a quick sense of how might you expect an inner potential to be negative? That's our first question to answer. Just give me no maths, nothing. Just give me a quick sense of why you can expect that, or how might you expect it. I'll give you a hint. There is potassium inside. I lost my chalk. There is potassium ions inside and there is potassium ions outside. There are sodium ions inside and there are sodium ions inside also, right? There is a sodium concentration inside and outside, potassium concentration inside and outside. My hint is this: suppose the sodium concentration is high outside, but the potassium concentration is high inside relative to the outside. Concentration is ion to ion, concentration, sodium is high outside, sodium concentration is high outside relative to the inside. Potassium concentration is high inside relative to the outside. Now can you give me a suggestion? How might you expect charge to be different? What is concentration got to do with charge? That's, even though these species are charged, how do you establish an electrical potential if all you get to play with is being able to set up concentration differences? That's the question. If potassium comes out, why is it coming out? Okay, good point. Yeah, it's not quite the pump, but yes, you're on the right track. If potassium is high on the outside, under a concentration gradient, it will try to pass through the channel, come down here, right? Unless the membrane specifically holds the concentration difference. There's a concentration gradient which will then cause a diffusive flux. Okay, that's what you're trying to say. Fine. So you will have a diffusive flux of potassium to outside. You'll have a diffusive flux due to concentration differences of sodium going inside. What then? They should balance off, but they don't. So if they don't balance off, well, how can you set up an electrical gradient? I'm sure all of you know the answer. I'm just trying to wake you up. Okay, here's how you might do it. Say that again. Reversing the direction. Okay, I'm not sure I understand. Let's take a look. Suppose you had only one species to worry about. Let's say you had, in a stylized sense, suppose you had just one positive species to worry about, right? And let's say you've drawn yourself a membrane with a high concentration of that species on this side and a low concentration of the species on this side. What will happen? We'll say that because of the concentration gradient, this is a concentration gradient, high here, low over here, there will be a diffusive flux over here. Okay, so let's say whatever it is causing a diffusion flux under concentration gradient, which will mean that if that happens, positive charge will pour out. If positive charge pours out, it leaves behind a deficit. So that means negative charge starts to build up on the inside. Correct? I mean, that makes sense, right? Negative relative to where you began with. Okay, I'm not saying that there's actual negative charge over here. I'm just saying there's more positive charge than here. So there's going to be a positive on this side and negative on that side, right? Which will then set up an electrical flux, because if there is going to be a buildup of potassium plus ions over here and negative charge here, and that will set up. So this is J diffusion due to a concentration gradient, which will set up a J electrical, simply because there is positive charge here, negative charge here, which will mean that then there will be an electric field from the positive to the negative, which will cause ions to go. So till when can this continue? Well, until the two are balanced off. Until the two are balanced off, which means that this will flow, and then there will be a flow in the opposite direction due to the electrical gradient being established, and they will keep going until the flow in this direction is balanced off by the flow in that direction, right? And when that occurs, that thing is called setting up a Nernst potential. There's an old equation called the Nernst-Planck equation, and it's a wonderful little exercise. Maybe I'll give it to you as one of the exercises, but I won't get into it right away. We'll do it as an exercise. What you're able to show is, ignore sodium for a minute. What you're able to show is if potassium is on the order of about 140 millimolar concentration on the inside, and the outside is on the order of about 5 to 10 millimolar concentration outside, then you can set up a reversal Nernst, a Nernst potential of about minus 85 millivolts on the inside. If, let me repeat that, if you maintain a high potassium concentration, about an order of magnitude or more inside relative to outside, you can set up a negative potential about on the order of minus about 85 millivolts relative to the outside. You can work out through these calculations. So I'll give you as an exercise, and you'll be able to show it relatively straightforwardly. Just a little calculation, quite an interesting calculation, right? It turns out that the reversal Nernst potential, I shouldn't call it reversal potential, I'll call it the Nernst potential, the potential inside to outside for which the fluxes are balanced, for which there is no net change no net further change. It's a dynamic equilibrium, right? There is a flux due to concentration difference over there, which is balanced by the flux due to the electrical field over there. That is proportional to the log of the concentration inside to the concentration outside. And I'll give you the exact expression in an exercise, right? So it is proportional to the concentration ratio, and you take a log of that, okay? And that gives you that potential that we are looking for. So for potassium, with the kinds of numbers I gave you, this is on the order of about minus 85 millivolts. That means if the potential inside was about minus 85 with the concentrations that I just told you, about 105 in the inside outside, then there would not be any net flux, no net flux, okay? So it's an electrochemical equilibrium. Does that make sense? Okay, so now you can do a little bit more to ask, well, if potassium is such and the sodium is also there, can you set up an electrical difference, electric potential difference? And the answer is yes, you can, right? And it turns out with high sodium here and low sodium concentration there, and high potassium concentration there and low sodium concentration there, you can actually set up minus 75 millivolts, or the cell does set up minus 75 millivolts resting potential. Okay. Why is what so? That's how biology has evolved. And it exploits a property of what is known as a sodium-potassium exchanger. A sodium-potassium exchanger is a transmembrane protein. It's a pump. It's a molecular machine, a little protein that constantly goes around throwing potassium and exchanging potassium and sodium. It separates sodium and potassium across the membrane. And as a consequence of that, which requires this ATP molecule, it keeps on doing it. As a constant consequence, it maintains potassium in concentration gradients like the ones I mentioned, which in turn gives rise to the electrical difference, membrane potential difference. Yeah, the last bit is you have to refine that a little bit. I'm saying they're both positive ions, but by maintaining relative concentrations of sodium and potassium inside and outside, you are able to get negative charge on the inside. Yeah? Well, they are positively charged ions. They have one, the valence is 1. So, one positive charge on the potassium, one positive charge on the sodium. Is that?
One positive of A is will more different from one positive of
No, 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 no. Charges are the same. That's one charge. Okay. Perhaps your confusion is how come there are no negative charges in this situation? Why are you able to set up a negative charge on the inside? Yeah. So we'll work through that exercise problem, which I see is now getting very interesting, and you will be able to see this. Okay. Yes, for a single ion. If you have one ion for which you're trying to explain it, you can use it through using the Nernst equilibrium potential or Nernst equation, right? If you have to explain more than one ion, sodium and potassium, then you have to switch to what is known as the Goldman-Hodgkin-Katz equation to explain what will be the effect of both sodium and potassium interacting together. Remember, the sodium and potassium cannot be completely independent. Even if I say that the ion channel corresponding to sodium is different from the ion channel corresponding to potassium, they are both linked to the potential inside. So together they will determine the potential inside. They are coupled. Sodium and potassium will be coupled, and therefore you have to enhance the, you have to generalize the idea of the Nernst equilibrium potential to the Goldman-Hodgkin-Katz equation. That there are well-developed theories for doing this. Okay. Any other question? I have about 15 minutes to go, right? Okay. I'll try and set up something interesting to do for tomorrow. Okay, so we are at this point where we feel we understand, or we will feel once we do the exercise in more detail, we understand where the electric potential can come from by having a concentration difference, concentration gradient set up across the membrane potential. Now we have to explain how can it be that we can get all of these wonderful exquisite changes in the membrane potential and so on. So that will involve understanding dynamics of what goes on inside these changes, which essentially means that we are going to now start writing ordinary differential equations for, what will we write them for? We will write them for how these membrane potentials can change in time. And why will they change in time? They will change for the following reason. These ion channels are voltage gated. It's a lovely, this is just a very fancy name for saying that if the voltage changes, if the membrane potential changes, the permeability of how easily ions can get across the channel changes. So the channel pore is actually dependent on the voltage that the cell has. Okay? And that's the meaning of what it means to say these are voltage gated. Remarkable and true, these channels can sense the voltage of the cell. So they change their pore size, or rather more, to be more careful about it, the permeability of the pore, the permeability of the channel, the permeability to that ion across the membrane in response to changes in the membrane potential itself. In response to changes of the cell, in response to the voltage change of the cell, these channels will change their pore size. So we have a twin problem. Not only are the membrane potentials what help you establish the potential, but if the potential changes, then those membrane properties also change, those ion channel properties also change, which means in turn the potential will change, which means that the ion channel properties will change, and so on and so forth. So we have to write differential equations to explain the whole process. Does this make sense? Right. Voltage is coupled to the gating properties. Voltage determines the gating properties of these channels, and the gating properties will determine the voltage as well. So it's a coupled system, and you have to write equations that describe the entire process. Does that make sense? Which in a sense, we are in one word, we are going to write differential equations. So what might be the differential equations that we are going to write? Clearly, one of the differential equations we are going to write is dV by dt. If you write a differential equation for the change in the membrane potential, that will be governed by some property in particular of the membrane potential itself, and we have to write down properties of, let's call it M, right? Some property of the membrane potential, which will then describe changes in the voltage, right? So our equations are going to have this form dV by dt, and I'm going to drop the subscript m to avoid writing it over and over with the understanding that you understand when I'm writing V, I actually mean the membrane potential Vm. Okay, so dm by dt will contain somehow dependence on the channel properties. Let's just call them m for now, and channel properties will also have a dependence on V, right? So it's a coupled system. You can see that this is, and of course V and m, V and m. Okay. So you will have a fully coupled system over here. Okay. So let's get started describing this. I remember I said to you that I started by saying that truly neuromorphic chips are not available at the moment, right? But what we have at the moment are equations that you can write down that will simulate this in a computer. You could, by the end of the week, you will by the end of the week actually write a simulation of all of the processes that are taking place. So even if we don't have neuromorphic chips, you're no less limited. You can write everything that you would want to write, you would want to do with that chip in a piece of software. So one of the tutorial sessions, I will show you a piece of software called XPP out, which will actually allow you to simulate this, right? So let's first start by understanding how might we write equations corresponding to the right hand sides of this, and whether we need more equations and so on, that will actually describe a perfect simulation of that process over here, that action potential over there. Okay, that's going to be the goal for the next couple of hours. Okay, so let me get you started. Let's think for a minute. These are electrical processes, right? Where might you begin? Where do you begin to do the modeling? How do we begin to model, which means think about how can we start to write the equations corresponding to this physiological process, right? For an applied mathematician, a model is if I can express whatever biological processes I need to express in an equation, that's my model. Okay. Where do you begin to model? Okay, you're not going to be able to do it without thinking of the physiology. You're going to have to think about the biology, but you also want to try and understand what are the properties of electrical circuits I might know that help me write down these equations. So we'll jump very quickly little bit into the stuff that we know about circuits. So everybody knows what a resistor is, or maybe you recall it. This is probably covered in 9th or 10th standard, right? So I'll go over these equations. If you don't know what it is, or if you want to know more about it, then you just talk to me later, right? If you have a resistor and you apply a voltage difference along it, you know, this is very straightforward to do. You can take a little breadboard, you find a resistor, take a little wire, take a little battery, connect it up, okay? Then the equation of the current that flows in the resistor, the current will flow from the high potential to the low potential. The current that flows is going to be V is equal to IR. Okay, the resistor is simply the proportionality of voltage to current relationship that develops between these two. Okay, does that make sense? Okay, you apply voltage, you get a current in proportion. That proportionality is called the resistance of this element. Okay, if you had a capacitor, this is the symbol for a capacitor, that's the symbol for a resistor. If you apply a voltage across it, if you apply a battery across it, does anybody remember the equation for a capacitor? Q is equal to CV. Is that what you're saying? So you're saying the charge on the capacitor is going to be proportional to the voltage you apply across it? That's correct? Correct? Okay. So if you differentiate this, you get dq by dt is dv by dt. Is that correct? Right? So dv by dt is c times, actually, I'm sorry, c dv by dt is I. dq by dt is I. The current that is passing through the capacitor, the current that passes through the capacitor is the rate of charge flow across this, right? The charge across the two plates of the capacitor. So that's dq by dt. So the equation corresponding to the capacitor is going to be C dV dt is I. The equation for resistor is going to be V is equal to IR, right? This is an algebraic equation, this is a differential equation. Okay. Now you can connect with these basic elements. You can add a capacitor to a resistor and then apply a voltage across the two of them. You can apply them in parallel and apply a voltage across them and so on. So now you can play games, and you can go figure out what the equation is. You can solve the equation. You can go to your neighborhood electronics shop, bring those circuits, put them together, and figure it out. You can evaluate whether your solution was right or wrong, whether your answer was right or wrong. Okay, so so we are going to write a differential equation along these lines, but first you have to figure out where are the resistors and where are the capacitors. This was the biological system. What resistors, what capacitors? Can I think of this system as being made up of resistors and capacitors? Okay, I will show you where that comes from, and then we'll stop and continue tomorrow. Okay, so quickly in the 5 minutes that we have, which aspect of this looks like a resistor to you? Which diffusion process of what, where? Okay, so there is something happening across the ion channel, some transfer of ions. Now, so you're saying this is a capacitor or a resistor? Okay, it's a resistor. That means if there is an electrical potential here, there will be a current proportional to some property of the ion channel. Is that what you're saying? Okay, so some resistance. So think of this as a resistor. Because there is an ion channel here, it is resisting the flow of current across the membrane, and that is correct. The answer is correct. So because there is an electrical potential here, right, and there is a current that will flow across, the resistance that is offered to that current because of this potential difference is the resistance of this ion channel. So yes, ion channels can be thought of as resistors because they resist the flow of current. I mean, they offer a certain resistance to the flow of current and allow current to go through. So that looks exactly like this circuit over here. Okay, what else? Can you think of capacitors? We are going to ignore volume changes in this system. It is true that for many systems, voltage changes can be associated with changes of volume, but we are going to change. This system will work without volume change. So we are going to ignore volume changes. It is not the physical swelling or shrinking of the membrane that's going to be interesting to us. So resistor we saw. Can anybody spot the capacitor here? Okay, so let me describe to you how a capacitor is actually made. At least in the old days, this is how it used to be made, right? And some of the new ones, I mean, some of the capacitors now also are made like this. If you take a plate, you take a conducting plate here and you take a corresponding conducting plate over there, separate them very closely by, and this medium is called a dielectric, something that does not allow electricity to go through, like oil or cardboard or something like that. You know, if this configuration creates a capacitor, because now you can take a potential, you can take a battery, attach it to these ends that will store charge and keep it stored for you. That configuration is a capacitor. Where do you see this over there? Is anybody can now you speak? Lipid bilayer. Okay, who said that? So where is it? Which aspect? Which are the plates of the capacitor and which is the lipid bilayer? Obviously, the lipid bilayer is this oily membrane. And why can you think of this as, that's your capacitor. Why can you, this is the medium, the dielectric filling the plates. Why are these things sort of plates? Because hydrophilic, yes, and yes. So what you're explaining to me is that this is an oil dielectric. Agreed. Why are these two sides thought of as plates of this capacitor that I drew? Why can they store charge? Because They are? Yes. Okay. Remember that I told you that this was an isopotential. So it's electrically equivalent to metal. You can flow very quickly in metal. You can flow very quickly in an aqueous solution, right? So think of this entire thing as one metallic plate. The entire think of this as a spherical capacitor, right? And the outside similarly is an aqueous solution. So it's an isopotential. What you need are metallic plates in order to create the isopotential here and an isopotential over there, and separate the two isopotentials with a lipid dielectric. And that's exactly what is occurring on this membrane over here, right? So you've got a capacitance that's associated with the membrane, and you've got a resistance that is associated with charge transfer taking place through the ions. Okay. So tomorrow I will put these two elements together to show you the differential equations, show you where the memristor is, right? It will arise in a special form that these equations take, and we will write the complete electrical circuit, which then we will simulate with the numbers that Hodgkin-Huxley showed us to actually get this. That's going to be the program for understanding how the Hodgkin-Huxley model is able to produce an action potential. Does that make sense? See where we are going? Okay, so I'll stop here.